In this project, the objective is to design and test circuitries for biomedical signal processing system. This is my patched circuit showing the 4 different stages. And these are the stages on the schematics. After editing the video, I realized that I have been connecting channel 1 of the oscilloscope to the output and channel 2 of the oscilloscope to the input of the circuit throughout the entire video. I've checked and ensured that even though the waveforms are switched, the values that I've obtained are still correct and that my circuit is still working properly. I apologize for my mistake. I will now be talking about the common components inside the whole circuit. There are 5 coupling capacitors in this whole circuit, namely C1, C4, C5, C8, and C13. The formula for the capacitor's resistance is 1 over 2 pi Fc, where F is the frequency of the signal and C is the capacitance value. The capacitor acts as an open circuit for DC signals passing through, because the limit of the reactance of a capacitor when F approaches 0 is infinity. Therefore, since the frequency of DC signals equals to 0 while AC is not, hence, the capacitor blocks DC signals and allows AC signals to pass through, as any DC input offset when amplified will create a larger output offset and will push the output towards one of the rails and reduces headroom. There are 3 sets of voltage dividers in this whole circuit, consisting of resistors R5, R6, R9, R10, R11, and R12. Since 9 volts is injected at VCC, the voltage that comes out of the voltage divider is 4.5 volts, with the AC signals sitting on top of it. It also acts as a level shifter to shift the waveform up during the single supply mode so that the negative half of the waveform will not be clipped off. The first stage, from test point 1 to test point 2, is a pre-amplifier stage, which uses TL072 IC and is a low-noise JFET dual operational amplifier. It uses a closed-loop, non-inverting amplifier to amplify the signals obtained from the microphone, with the input and output voltages being in phase. It also gives us a passband gain of 23 by substituting R2 and R3 into the formula. Since pin 4 of the IC is connected to the ground instead of V-, its internal reference is now set to half VCC. The resistor R2, R3, and capacitor C2, C3 forms a band-pass filter. The resistor R2 and capacitor C2 forms a passive low-pass filter and gives a high cutoff frequency value of 1.064 kHz when substituting the value of R2 and C2 into the formula. The resistor R3 and capacitor C3 forms a passive high-pass filter and gives a low cutoff frequency of 15.9 Hz when substituting the values of R3 and R4 into the formula. I calculated the bandwidth of this bandpass filter by subtracting the high cutoff frequency and low cutoff frequency to give us a value of 1.048 kHz. And I used the formula of center frequency to get a value of 130 Hz. I also divided the center frequency with the bandwidth to give its quality factor of 0.124, and its Q factor being less than 10, this is a wideband filter. We can see that as frequency increases, its gain also increases until it hits 23, before it starts dropping, and it is the same as the passband gain that I calculated beforehand. This graph shows the frequency response curve, and by drawing the negative 3 dB line, we know that the low cutoff frequency is 20 Hz and the high cutoff frequency is 1500 Hz. By using the formulas, I can deduce that the bandwidth is 1480 Hz, the center frequency is 173 Hz, and the Q factor is 0.115, which are all similar to the previously calculated values, hence indicating that my circuit is working properly. Connect the function generator to Vin. Check that the function gen load is set to high Z, which can be done by pressing Utility, Output Setup, then select high Z. Set the output waveform to sine wave by pressing on the sine button. Next, set the frequency to 100 Hz. By pressing on frequency, type out 100 onto the keypad and then select Hertz. Then, set the amplitude to 200 mV peak to peak, which can be done by pressing the amplitude, type out 200 on the keypad, and then select millivolts peak to peak. Once everything is set, you can hit the output button to inject the load into the circuit. To test stage 1, connect the probe of channel 1 to test point 1 and the output to test point 2. The trigger knob helps to stabilize the waveform on the oscilloscope. You can stabilize the waveform display by setting the trigger of channel with a bigger waveform, in this case channel 2. To change the volt per division, you can turn this knob for channel 1 and this knob for channel 2. To adjust the time per division, we turn this knob. To find out Vin and Vout, press the measure button and the values will appear at the bottom of the screen. The second stage, from test point 2 to test point 3, is a negative feedback loop amplifier, which has a 100 kilo ohm potentiometer connected to it to control the output gain from stage 1. The second stage uses a closed loop inverting amplifier, and hence will give an output voltage that is 180 degrees out of phase to the input voltage. By substituting P1 and R4 into the gain formula, we can get a minimum gain of 0 and a maximum gain of negative 10. However, if we turn the trimmer all the way, the gain will be too high and will get clipped off at some point. To test stage 2, put the probe of channel 1 to test point 2 and channel 2 to test point 3. The connection of the power supply and the function gen is the same as before. Based on the oscilloscope, the output waveform is 180 degrees out of phase to the input waveform. When the potentiometer is set at 0 ohms, the waveform shown is a straight line, indicating a gain of 0. By turning the potentiometer, the resistance increases so as the gain, and displaying a sine wave on the oscilloscope. By turning the potentiometer to its max resistance, the waveform will end up being clipped off. Since the outcome is as expected, my stage 2 of this circuit is most likely correct. The third stage, from test point 3 to test point 4, is a Sallen-Key second-order low-pass filter, which removes high frequency from the audio signal and allow low-frequency signals to pass through. Resistors are connected before the capacitors to make this a passive low-pass filter, and two pairs of it connected to a closed-loop non-inverting op-amp makes it a Sallen-Key second-order low-pass filter. By substituting R7, R8, C6, and C7 into the cutoff frequency formula, we get a value of 1023 Hz. And since the low cutoff frequency is 0, We can get a bandwidth of 1023 Hz by subtracting the high cutoff frequency with the low cutoff frequency. There are two ways to test stage 3. The first method is to adjust the trimmer at stage 2, and the second method is to connect the function gen straight to the third stage, with the amplitude being 5V peak to peak. I will be using the second method to collect my data as it is more accurate. I got a voltage of 3.6 with the function gen set to 1000 Hz, and I will be repeating this individually from 20 Hz all the way to 4000 Hz. These are my values obtained from the circuit, and this is my frequency response graph drawn. We can deduce that it has unity gain until it reaches 100 Hz and decreases as the frequency increases. By drawing the negative 3 dB line, we know that the cutoff frequency is 1200 Hz, and since it is roughly similar to the previously calculated value, it tells me that my circuit is working properly. Connect the input of the oscilloscope to test point 3, with the function gen being set to 200 mV peak to peak. When we turn the potentiometer in stage 2 to the minimum resistance, the waveform shows a straight line. Increasing the resistance will cause the VPP to increase and eventually be clipped off. This indicates that my circuit is working properly. The fourth stage, from test point 4 to test point 5, is an audio amplifier, which amplifies the audio signals and has a potentiometer to control the overall gain within this stage. It uses LM386N IC, which is a low voltage power amplifier. It is the only op-amp in this whole circuit that also amplifies current and does not require a voltage divider, because it is made to be working in a single supply mode internally. As shown on the LM386 datasheet, the audio amplifier produces a gain of 20 and has a load impedance ranging from 4 to 32 ohms. The potentiometer helps to control the overall gain from the previous stages by reducing the signals down before entering stage 4. Capacitor C15 and resistor R17 forms a Zobel network which uses a low-pass filter. A Zobel network is a series resistor-capacitor network that is connected in parallel with a loudspeaker driver in order to neutralize the effects of the driver voice coil inductance. Capacitor C13 is still a coupling capacitor, but uses a higher capacitance value than the rest to reduce the reactance and allow low-frequency signals to pass through it. After calculating the reactance of capacitor C13, it gives us a value of 14 ohms, which fits well within the load impedance range of the LM386N IC. To test stage 4, place the probe of channel 1 at test point 4 and channel 2 to test point 5. The connection for the power supply and function gen remains the same as the previous stages. When the potentiometer is set to the maximum resistance, the output waveform shows a straight line. Reducing the resistance of the potentiometer causes the gain to increase and eventually be clipped off. We can connect the probe of channel 1 to pin 3 of the IC and calculate the gain of the audio amplifier by dividing the value of the Vout and Vin, giving us a gain of 19.8. Since the gain is as expected, my circuit is working properly. In conclusion, this circuit has 4 stages to amplify one subbeat and a microphone and allow the users to hear it at the output. The first stage is a pre-amplifier circuit, which uses a closed-loop, non-inverting amplifier to amplify the signals obtained from the microphone to line level. The second stage is a negative feedback loop amplifier, which has a 100 kilo-ohm potentiometer connected to it to control the gain and can also act as a linear amplifier. The third stage is a Sallen-Key second-order low-pass filter, which removes noise by rejecting high frequencies from the audio signal and allow low-frequency signals to pass through. The fourth stage, which is an audio amplifier, amplifies the voltage and current so that the user is able to hear the heartbeat at the output. One mistake I made was by connecting capacitor C15 vertically, resulting in a short circuit. I ended up burning both the IC and the resistor R17. After correcting my mistake, my circuit was no longer producing smoke and was working properly.